it's Mrs. Smith, and we are back to learning and getting back to the new normal, I guess. I hope that all of you are doing well and you are staying healthy and safe with your families. We all have different situations that we're managing, and we can only do the best that we can do. So I just want to say that I miss you all. I miss being in class. Miss being my goofy self and just seeing everyone day to day, and hoping you're all managing okay. So this too shall pass. We'll be back to what we know before we know it. So we just have to keep pushing. So we are going to learn something new today, and that topic is going to be in chapter 10. So you might be thinking, oh my gosh, how do we get from chapter 6 to chapter 10? This is actually an order that we've normally gone in past years with Algebra 1. We take a look at radicals, because radicals are important for really chapter 8, and even thinking a little bit in chapter 7 when you look at patterns. And so all of the algebra classes are doing this topic next. We did finish chapter 6. We didn't have a celebration of knowledge on chapter 6. We're not going to have a celebration of knowledge on chapter 6. We're just going to move to section 10.2. So we're going to do 2 sections in chapter 10, and then we're going to go back to chapter 7. And the only 2 sections in chapter 10 will be 10.2 and 10.3. These are super important sections for geometry, and you're going to want to make sure that you learn this so that you know how to do it when you apply in geometry next year. So we're going to talk about radicals. So a radical is a root. People call it a root. And what is that? It's kind of weird, right? It's kind of weird. It's not like a root on a tree, right? It is a root that could be a square root, it could be a cube root, it could be a 4th root, it could be a 5th root. We're going to focus on square roots. So when we say the square root of some number, let me just think of one that works out nicely, 25. What you're asking yourself is, what times itself will equal the number on the inside, 25? And we know that 5 times 5 equals 25, so the square root of 25 is 5. This is a calculation we could do on our calculator. You have the square root button. And this we would call a perfect square. So a perfect square is a number that is created by multiplying an integer by itself. So we have a list of perfect squares we could create just by saying 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. We could come up with a whole list of perfect squares. Okay. So this is a list of perfect squares, and the square root of every single one of these numbers would be equal to an integer. Now, if we had a number inside this radical, this root, that was not a perfect square, if we take that square root on the calculator, we're going to get a decimal that is very long, and in fact, it goes on forever and there's no repeats. So if we had, let's say, the square root of my lucky number 26, then I would have to say that it's approximately equal to, and I would assume that it's 5 point something, 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 something. Okay, I don't know what it is off the top of my head. This kind of answer as a decimal is not what we want when we do a perfect square. Okay, I could estimate that it's somewhere between 5 and 6, because the square root of 26 is between the square root of 25 and the square root of 36. Right, so it has to be somewhere between 5 and 6. Well, we don't want these decimal values. We want to be able to write a square root in what's called simple radical form. Simple radical form. So we're going to talk about how to do that. So let's say we had the square root of 72. Square root of 72 does not just equal an integer, because I know that 72 is not a perfect square. 72 is between the perfect squares 64 and 81. So the square root of 72 is probably, as a decimal, is probably, again, 8 point something. But I don't want this answer. I don't want you to just do that on a calculator. We want to rewrite this in something called simple radical form. What is simple radical form? Well, simple radical form is a method of kind of pulling out perfect squares. So we can do that in one of two ways. All right, I've taught this in both ways, and I'm going to show you both methods, and as always, I'm going to trust that you're going to pick the method that works for you. And so one method is to figure out the largest perfect square that divides evenly into the number. Okay, so I know, just because I made this one up off the top of my head, that 72 is 36 times 2. Now 36 is a perfect square, okay? And there's a property that says that we can break these square roots apart. So we could rewrite this as the square root of 6 times the square root of 2. So that in fact is a property. That if you have a product, you can break it into the product of two individual radicals. So we could say, well, the square root of 36 is 6, and the square root of 2, well, that can't be simplified because 2 is not a perfect square, and there aren't any other factors that are perfect squares of the number 2. Okay. So this answer right here, this 6 times the square root of 2, is the simple radical form of the square root of 72. Now that's great if you can identify the perfect square that is a factor of the number you're trying to take the square root of. But we really don't always know that. So there's another way to do it. And I found that students can be very successful with this method. And it really is about kind of breaking it up into what's called its prime factorization. So do you know what a prime number is? Right? A prime number is a number whose only factors are 1 in itself. Can't break it up anymore, right? And the factorization means that we're going to rewrite this number as a product, right? Product of its factors. So we're rewriting it as a product of its prime factors. So this might look really long when I do this first, but once you get the hang of it, it can go very quickly, all right? So we're going to take 72 and we're going to make a factor tree. Right, so I know that 72 is, let me see, 8 times 9, right, is one way. So you can start this off in many different ways. Now 8 is not a prime number. I can break up 8 into 2 times 4. And I can break up 4 into 2 times 2. All of these are prime numbers, right? Well, they're all the same prime number too, so I can stop at this point. But 9 is not prime because it can be written as 3 times 3. So using this property, we can say that the square root of 72 is the same as the square root of 2 times 2 times 2 times 3 times 3. So I've got all these prime numbers here. Right? I'm not circling the 4, the 8, and the 9 because they're not prime. And I actually broke those up even more. So I've got these prime factors of 72, and that allows me to create perfect squares, because perfect squares are easy to take the square root of, right? So when I circle a pair of numbers, I'm creating a perfect square. So I've got a 2 times 2, and I've got a 3 times 3. So I could rewrite this as the square root of 4 times 9 times, I'm going to put the 2 last. And because we can break this apart, we can rewrite this as the square root of 4 times the square root of 9 times the square root of 2. And so at this point, we could say that the square root of 4 is equal to 2. And the square root of 9 is equal to 3. And the square root of 2, well, you know what? I can't do anything with that. So we have, we've got a 2 times a 3 times the square root of 2, which is 2 times 3 is 6, 6 square roots of 2. So all of this in between here is my explanation of how to get here, right? Sometimes students just make the tree and then they say, well, for every pair I'm going to take out 1 because I've just created that perfect square. So the square root of 9 is 3, the square root of 4 is 2. For every pair you take out 1, and then the leftover, sometimes I put a square around it. The leftovers go back inside. Okay? Let me try another one of those just to show you that method again. And once again, if you know your perfect squares, all right, you can do it by that method that I showed first. But this is kind of a tried and true method that many students find success with. All right, so let me think of one. Let's see. I'm gonna do the square root of what about the square root of 24? Square root of 24. So again, I know it's not just an integer because 24 is not a perfect square. I can't multiply a number by itself and get 24. But I can break up 24 and pull out perfect squares. So I'm going to make a tree, and I'm just going to start, because I know it ends in an even number, divide it by 2. So that's 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So I have all my primes. So I'm circling a pair because that's making a perfect square. These two are left over. So 24 is really 4 times 2 times 3. And the square root of 4 is 2. And the square root of 2 can't be simplified, so I just multiply these two together to get 2 square roots of 6, or 2 root 6. So this is the simple radical form of the square root of 24. Now we can simplify radicals, but we could also multiply them, and we could also divide them. So similar to this property for multiplication, if we had a problem where we had division, then we could separate them into the square root of a divided by the square root of b. Okay, so these are two properties that you'd want to have in your notes. Okay, if you're numbering your examples, I think I'm on example 3. I'm sorry, I'm not formally numbering them. Okay, but you're going to do what you need to do. Some of you really do like to take notes, and this certainly would be a good reference point while you work on your problems. Okay, so let's try to look at just a couple problems with these properties here, okay? Let's say we had 8 square roots of 2 divided by 2 square roots of 8. So we just kind of swap them, okay? If we wanted to divide these two, right, we could put the numbers that are in the radical together, right? So we could think of this as 8 divided by 2 times the square root of 2 divided by 8. So we would just divide this as we normally do, or reduce fractions. 8 divided by 2 is 4. And then this would be the square root of 1/4. We could put this back together if we wanted to. We could say this is the square root of 1 over the square root of 4. And that can be simplified to 1 over 2. Don't forget, this is multiplication. 4 times 1/2 is 2. Because it's 4 over 1 times 1 over 2. Okay. So we can divide radicals, right? And we can multiply radicals, right? We haven't done one where we multiplied them, but it's the same idea. So I'll do one of those. And then I just have one more problem I want to show you after this, okay? All right, so let's say we had 2 square roots of 7 times 3 square roots of, let's say 21, okay? So these by themselves cannot be simplified because 7 is not a perfect square. It doesn't have any perfect squares as factors. 21 is not a perfect square. It doesn't have any factors that are perfect squares. So really, the best bet would be to multiply these to see if we can create any common factors. So we would multiply the outsides with the outsides and the insides with the insides. Okay, so that would be 6 times the square root of, I think that's 147. Now I don't want to stop here, even though I have multiplied, right? Because 147 has some perfect squares in it. And I know that I started out with 7 times 21, so I know that there must be a perfect square in here because this has a 7 in it too, right? So I'm going to break it up. 7 times 21, that's how I got it. And 21 is 7 times 3. So in a problem like this, right, and once again, I circle the pair because that creates a perfect square. And I put a square around the leftover, okay? So this 6 is still hanging out here, so it's going to be 6 times whatever this is. So the square root of 147 is a pair of 7s, so for each pair you take out 1 and you put the leftover back inside, right? Because essentially I'm saying that 147 is the square root of 49 times the square root of 3. Now, this is 6 times 7 square roots of 3, so I'd want to multiply the 6 and the 7 because they're on the outside of the radical. So 6 times 7 is 42, 42 square roots of 3. And that would be the answer for this product. Okay, there's one last concept, and you're going to be able to ask me a whole bunch of questions during a Zoom. So if you're feeling like, oh my gosh, right, we're still going to have other time to learn this week, okay? You're going to give it your best shot. So let's say we had 2 divided by the square root of 3. You might be thinking, well, you really can't do much with that because the square root of 3, right, that can't be simplified. And we can't divide anything here because we have one in a radical, the other one's not in a radical. So what could you do for that? Well, in mathematics, a fraction is not simplified if it has a radical in the denominator, on the bottom. So we need to figure out a way to not have a radical in the bottom of this fraction. Now, if we think about when we reduce or simplify fractions, normally, right, if you had something like 4/8, you would divide the top and bottom by 4 to reduce it or simplify it. You'd make it look different, but it still means the same thing. So this is the same idea. We can multiply the same number on top and bottom, we can divide the same number, and so we need to figure out a way to do that in a problem like this. Well, dividing's not going to help, but if we multiply by the same square root, then we're going to get something that is not any longer a square root if we simplify it. So the square root of 3 times the square root of 3 is the square root of 9. 2 times the square root of 3 is 2 root 3. And this can be simplified because the square root of 9 is 3. So we would have 2 square roots of 3 divided by 3. So this is called rationalizing. Rationalizing the denominator. Okay. So I've covered a lot in a short amount of time, I know that, and we're going to work on this topic this week. I'm going to post a worksheet with some practice problems and the answer key. I'd like you to work on those, and I'd like you to bring any questions that you may have to either Zoom meeting that I offer this week. Okay, look for the invite on Schoology. Thanks a lot, folks, and have a great day.